We're taking one more step in our idea of probability today. We're going to move to compound events, and I've split this up into 2 different days. Day 1, we're going to talk about conditional probability and the multiplication rules. Conditional probability just has to do with whether the conditions of one event might affect the outcome of another. When we talk about independent events, we would say that the outcome of one event does not change the probability for the other event. And a good example of that would be flipping a coin and rolling a die. The outcome of the coin does not affect the probability of how the die is going to land. Remember that our sample space includes those 12 simple events, and if we wanted to find the probability that you flipped a tail and you rolled a number less than 3, we would have 2 outcomes that match that event. So we could say the probability that you get a tail and a number less than 3 would be 2 out of 12 or 1/6. That's an example of a compound event because we're talking about something happening and something happening in sequence. You'll hear me say this a lot, that the word "and" means multiply in probability. And means multiply. And it's just as simple as that for independent events. If I were finding the probability of A and B happening, I would just take the probability of A times the probability of B. What's the probability of flipping heads? 1 out of 2. What's the probability of rolling an even? There's 3 evens out of 6, so we could say that's also 1 out of 2. And so what's the probability of flipping heads and rolling an even number? Since those are independent, we can simply take the probability of heads times the probability of an even number, and this would be the probability that you get heads and an even number. I would also say that your gender and which lunch you eat are independent events. So let's try to estimate this. Let's say that at Shanley, the probability of being a girl is 50%. And since there's 3 lunches, and this might not be super accurate, but maybe the probability of eating first lunch is 33%. Since those would be considered independent events, we can say that the probability of being a girl and having first lunch is simply the probability of being a girl times the probability of having first lunch. And you should notice that that probability is lower than either of those things happening just all by themselves, because as you add more and more stipulations, more and more criteria, the probability naturally goes down. Now, dependent events gets a little trickier. The outcome of one event changes the probability for the other event. So here's an example. When we talk about Shanley students being in statistics and being seniors, we know that seniors take statistics more than other students do, and that's why these would be considered dependent events. So let's make up some numbers again. The probability of taking statistics. Well, this year I've got 20 students in statistics, and how many students in the school? Should we just say 350? I'm estimating. Randomly selecting a senior from Shanley. Last time I checked, there were 94 seniors, so we'll say 94 out of 350. Now, what's the probability of being in statistics times the probability of being a senior? So that comes out to 1.5%. Now let's think about the probability that we randomly select a Shanley student and that person is in statistics and is a senior. We'd be out of 350 students, but then we'd want to think how many people are in statistics and are seniors. It turns out we have 2 juniors this year, and so there are 18 people in this school who are in statistics who are also seniors. So that probability is 5.1%. We didn't need a formula to calculate that. We just used our common sense. We used the numbers that we understand. And for most problems, that's how you'll be able to do these. But if you do need to use a formula, remember how I said and means multiply? Well, that doesn't work in this situation. And the reason is that we're not talking about independent events this time. We're talking about dependent events. So for dependent events, if we wanted to use a formula, we would need something new. And these are the formulas that we use for dependent events. If we want to find the probability that A and B happen, this is what this means. We would take the probability of A times the probability of B, but this notation means we'd have to consider that A already happened. Same thing, we could do it in the other order instead. We could take the probability of B times the probability of A, but in that case we'd want to consider the probability of A given that B has already happened, because remember, the outcome of one is going to affect the probability of the other. So this vertical line in that notation is read as given that something else has already happened. So if I were to take the probability that someone's in statistics times the probability that they're a senior, that should tell me the probability that they're in statistics and are a senior, as long as we factor in that we've already given that we've chosen a statistics student. Let's see if we can figure this out. So once again, the probability of being in statistics is 20 out of 350. We're going to take that times the probability of senior. Now, the probability of senior was 94 out of 350, but we have to consider the fact that we've already narrowed it down. It's already given that we're looking at a stats student. So if we've narrowed it down to only stats students, then what's the probability of finding a senior? We've narrowed it down to only our stats students. That affects the denominator. And what's the probability that we find a senior in class? There are 18 of them. And you'll notice if you take a 20 divided by a 20, that's 1, and we get that 18 out of 350. And we had figured that out on the previous slide just by using common sense, but this is how the formula would work. And did you know we could do that in the opposite order too? We could take the probability of senior times the probability of statistics given senior. That's how we read that, the probability that someone is in statistics given that they are a senior. Let's see how this one would work. First of all, the probability of choosing a senior out of the student body times the probability of choosing a stats student given that we've already narrowed it down to only seniors. If we'd narrowed it down to only seniors, that affects our denominator. So you could almost, sometimes I think of that vertical line as sort of representing a fraction. That thing that is given is going to affect our denominator. So how many seniors are there? There are 94. And out of those 94 seniors, what's the probability you're going to find somebody who's in stats? Well, there are 18 seniors in stats, so that would be an 18 out of 94 chance. Again, that's going to simplify to 18 out of 350. And so this formula is a way to make that multiplication rule work again. Remember, and means multiply. And means multiply. But we just have to think a little harder about what we're multiplying by for dependent events. We're going to talk about playing cards once in a while, so it might be helpful just for you to, if you're not a card person, know what a standard deck looks like. A standard deck has 52 cards. You'll notice that there's 4 of each number. There are 13 of each suit, they call it. Jacks, queens, and kings are called face cards. So just some basics about what a standard deck of cards looks like. So in this card problem, what is the probability of being dealt the Queen of Hearts and then without replacement being dealt another heart? That whole thing about without replacement means that the deck is going to change for that second draw, and that's what makes these dependent events. So we are looking for the probability of being dealt the Queen of Hearts and then being dealt another heart. Since these are dependent events, I'm going to use that formula. Probability of Queen of Hearts times probability of hearts, given that the Queen of Hearts has already been dealt. So the probability of being given the Queen of Hearts, there's only one of those in the deck out of the 52 cards. And now the probability of a heart would normally be that there's 13 hearts in the deck out of 52, but we're given the information that the Queen of Hearts has already been taken. So we're down to only 51 cards in the deck, and since the Queen of Hearts is gone, there would only be 12 instead of 13 hearts left in the deck. And there's only about a 0.5% chance of that happening. We know that and means multiply in probability, but this will extend to multiple events too, as long as with each probability you're thinking about whether they're dependent. So here's the question: is it your lucky day? First, in your English class, you didn't have to present. And then it was your favorite lunch, which only happens once every 3 weeks. And then you won a coin toss and you didn't have to do the dishes at night. What are the chances? So this is multiple events, but we would consider them happening one after another, and so that would be an and sort of situation. I'm thinking that these would be independent events because presentations and lunches and doing the dishes at home would not really change the probability of each other. So we should be able to simply take the probability of each and multiply them. So probability of not having to present, 2 out of the 20 had to, so the complement of that would be you were one of 18 out of 20, and means times. It's your favorite lunch. It only happens once every 3 weeks. I'm assuming this is a school lunch thing in a normal year, so that would be 15 school days, and it only happens once every 15 school days. Pretty lucky. And then you won the coin toss so that you didn't have to do the dishes. We multiply straight across. And that's a 3% chance of all of those things happening on the same day, so that's a pretty lucky day. Finally, I wanted to go over that notation some more because I think that if you can get the notation down, that's going to help you on some of these more complicated problems. So this example, the event A is being a soccer player, and event B is being over 6 feet tall, and we are going to first of all write the notation for the probability of a soccer player being over 6 feet tall. So we're going to say the probability of. Now, if we look at how this is worded, it's probably better to rephrase it a little bit. The probability of being over 6 feet tall is what we're really looking for. And the fact that we're a soccer player has just sort of narrowed down the field, right? We're only looking at soccer players. So the way that we would write this is we are finding the probability of being over 6 feet tall, that's B, given that we've narrowed it down to only soccer players. We're only considering soccer players. The probability of B given A. The probability of a person being 6 feet tall or shorter and being a soccer player. So 6 feet tall or shorter, that's the opposite of B, right? What do we call opposite in probability? The complement. So B complement would stand for being 6 feet tall or under. And this was just a simple and, wasn't it? And, we're literally going to use the word and, being a soccer player is represented by A. The probability of a person 6 feet tall or shorter being a soccer player. So we've again narrowed down that field, right? We're only talking about the short people, and we're finding the probability of them being soccer players. So we're finding the probability of them being a soccer player given that they're 6 feet tall or shorter, which again was B complement. the probability of a person being over 6 feet tall or being a soccer player. So over 6 feet tall is just simply B. And this has the word or, which is another type of probability we'll talk more about in the future, or a soccer player. The probability of a non-soccer player being 6 feet tall or shorter. Do you recognize this as one where we've narrowed it down and we're only interested in non-soccer players, and we're finding the probability of them being short? So we want to think about, what am I finding the probability of? I'm finding the probability of them being short. Given that I've narrowed it down to non-soccer players, which is the complement of being a soccer player. Again, sometimes this notation is really going to help you understand what you need to do to find those calculations. And sometimes you'll be able to figure them out just sort of using common sense and thinking about how one affects the other.